to, I think Nikita, you had difficulties logging in to the Google Drive, which I'll talk about, and Jacob I'll touch base with you regarding the booklets and such. Okay, good. All right, let me share my screen. How's everyone else's week been? I've asked Sid, who had a long week, but hopefully the rest of you haven't had it too bad. Did anyone learn anything interesting in chem at school? What are you all up to right now? Jacob, what are you learning right now at school?
We've basically finished module 5 now. So we're just doing some like revision and stuff and then preparing. So my test is on Friday. So we're just kind of preparing for that.
Okay. Cool. Yeah, and just quickly update you, Jacob, regarding your booklet. It's still in transit, but you definitely should get it by Monday, Tuesday. If not, just give me a call. And but that shouldn't be the case. You definitely will get it by Monday, Tuesday, okay? And I think that's the case for most of you. You haven't got your booklets. I think with Tanya, you would have gotten your booklets by now, but the rest of you, most of you will get it on Monday. Good. All right. We've done quite a lot of K questions. We've done quite a lot of Q questions. Just quickly remind us, actually, though, what is K and Q? What are they referring to? And when do we use them?
So K is K, we can say that it's like the equilibrium constant.
Nice.
And was it? Yeah, so the equilibrium constant that we find out to find like where, like what in the reaction that the reaction needs to go to, was it?
Not quite. So K is just the equilibrium constant, and it's a value that an equilibrium will eventually reach at a temperature. That's quite literally it, right? Q, which is a reaction quotient, is what you compare to K to determine if a system's at equilibrium or not. Okay, pretty much Q is what you use when you don't know whether the system's at equilibrium and you want to find out. When Q is equal to K, system's at equilibrium. Nikita, what does it mean if Q is bigger than K? Is the system at equilibrium, which reaction would be favored?
The reverse reaction.
Good. So is the system at equilibrium though?
No.
Good. And what about if Q is smaller than K, Sid? Which reaction would be favored to reach equilibrium?
The forward reaction.
Very good. All right, so that's crucially it. And we've done some rice table questions. Final one, Rithania, when do you know to use a rice table? What kind of questions or what part of a question will tell you I need to use a rice table to solve this?
When concentrations in 2 different time points are given.
Very good. Very good. You're doing really good. All right, let me scroll all the way up because I think these are all just trial questions. And let's go and do some KSP questions, solution equilibrium. So we finished all of this. Okay, last thing I will mention is KEQ when we're talking about ionic substances and when we're talking about acids and bases. So when we're talking about ionic substances, the first most important thing you need to know is the way we write ionic dissolutions is a little bit different in year 12, right? So the way you're going to write it is you'll always write the solid on the left-hand side and the ions on the right-hand side. So an example would be if I was to give you PbCl2, right, which is an ionic substance. How do we know, Nikita, it's an ionic substance? What is the definition of a salt?
It has a okay, wait. So it has a okay, I don't know.
That's all right. But that's why we're here, right? We need to make sure we understand the basics and the foundation. Sid, on to you. What's the definition of ionic substance?
Is it when it's just a cation and anion joined together?
Very good, right? So usually it's a metal and a non-metal, but Sid's actually right. Sometimes, I'll give you an example, NH4Cl, Sid, is there a metal here?
Ammonia.
Is ammonia a metal, Sid?
Not a metal. Yeah.
Good.
So it's just
It's not a metal, and however, even though it's not a metal, we can see ammonia is a polyatomic ion. It's an example of a positive ion. The chloride is Cl minus, a negative ion, and since there is a cation and anion, we call it an ionic substance, right? And the bond between the cation and anion is what's called an electrostatic bond of attraction. That is a definition of ionic substance. So Sid's definition is the formal correct one, but usually it's when a metal and a non-metal are bound together, okay? So another hint, hopefully all of you are coming to class with a chemistry data sheet. If not, print it out ASAP. Can you guys hit the raise hand icon if you've got the data sheet in front of you now? If you don't, that's fine. I just want to know who's got it, just because, okay, those of you who don't have it, Google it right now, HSC NASA chemistry data sheet. Scroll through it, and Rithania, on the second or the back page of your data sheet, what do you see written? Just describe to everyone. It's on the back page of your data sheet.
Solubility constants?
Solubility constants, right? Now, little tip for all of you. Every single salt or ionic substance that's written on the back of that data sheet is insoluble. Okay, so to have what's called a solubility constant, you need to be insoluble as a salt. We'll talk about all of that much later. That's just a little point. The reason I mention that is some of you might be wondering, how do I know if lead chloride is solid, a liquid, aqueous, you know, when it's in water? It's a solid because it's insoluble, and to check that, just look at the back of your data sheet, you'll see PbCl2. Okay, but the way we write it is we write it with the solid on the left-hand side, and the right-hand side, we write the ions. And the reason for this, guys, is when I'm to find the K constant of this reaction, I will then know, well, what is a K constant? I'm going to pause for a moment and get you all to tell me. Actually, though, what is the K constant or the equilibrium constant for the reaction that I've just written? What's the expression for K, Akshita? Lead chloride.
So it was products over reactants. So the product would be PbCl2.
Is the product on the left-hand side or is the reactant on the left-hand side?
The products on the right-hand side.
Yeah, okay, so be very careful there. So again, start again. K is products over reactants. So who are the products?
So the products would be the Pb2+ and then the chloride, and then on below that would be the PbCl2.
Pause for a moment. What are you going to put or raise chloride to the power of? So it shouldn't be 4. It should have written 2.
So it would be raised to 2.
Good. All right. And then what would you do next?
And then on the bottom would be the PbCl2.
Okay. Okay. Now I want all of you to make sure you do this. Every time you make any, even any kind of mistake in HSC Chem, get a red pen and circle that mistake and write the correct answer. The secret to doing well in Chem is to making as many mistakes as you can in class with me. So when you go to school and you sit your exam, you don't fumble at all. And that's how you do well in Chem, right? Just not repeating the same mistake. So do you agree with the K constant? Correct?
yes. Yeah, I agree with that.
Okay. Rithania, do you agree with that K constant?
No.
Okay, I like this contention. A bit of drama in chemistry class. Jacob, do you agree with the K constant?
Nah, because it's a solid.
Good, right. So just a very small point, as Jacob mentioned. PbCl2 is a solid, so you do not add it on the denominator or as a reactant. So in actuality, the K constant for this reaction is just Pb2+ times Cl minus squared, right? The reason I mention this is because if you were to write the equation as Pb2 plus 2Cl minus gives you PbCl2, which is what some of you might be used to writing precipitation reactions or solubility reactions as, when you get K, your K is going to look funky. It's going to look like this. And first of all, this is not convention and it's wrong. But second of all, when you start doing calculation questions in terms of K, they're going to get much, much harder if you do it like this. So first point of principle that I'm getting across here is when it comes to ionic solutions, you always put the solid on the left-hand side. And when you write your K constant equation, you do not include the solid. Very, very important. Okay, those are the two caveats so far until we get to the next inquiry question, which is about KSP. Okay, good. That's all you need to know about ionic substances for now. Let's talk about dissociation of acids and bases. And first of all, what does this word mean, dissociation? Let's go to Jacob. Jacob, how would you define dissociation?
Is it just when like a compound kind of breaks down and separates into like the separate ions? It's like a solid turning into like the separate ions.
Good. So then my next question would be, what's the difference between dissociation and ionization?
I'm guessing maybe it's the opposite, where ions turn into a solid, or
close.
Yeah.
It's actually the same thing when it comes to dissociation, right? I just wanted to see to make sure that we're all comfortable in using the right words and terminology. The word that is different that you can't interchange, however, is the word dissolution. Dissolution just means dissolving in water. It has nothing to do with breaking apart into individual units or ions, which is what dissociation or ionization means, right? Ionization is telling you ionization means to form something, so forming ions. Dissociation is breaking apart. They mean the same thing, okay? It's how we describe salts in water. They will break up into their individual ions. Now, dissolution, an example would be if you have coffee or if you have, sugar in water. The sugar disappears because it dissolves in the water, but the actual sugar molecule, which is this hexagonal ring of hydrocarbons connected to more hexagonal rings, never breaks apart. It stays as either single ring, double ringed, or 10 rings of sugar, right? So dissolution and dissociation are two different things. Ionic substances dissolve and dissociate. Sugars and non-ionic substances that are soluble only dissolve. Does that make sense, everyone? Good. So just make sure you understand the terminology. Now, when we're talking about acids and bases, first of all, what is our definition of an acid? What is our definition of a base? Britannia, what do you think? What is an acid? What is a base?
The pH level of an acid would be less than 4.
Less than 7.
Less than 7,
good.
And
but
a base of 1.
Yeah, I like your description, but do you agree that's a bit more of a description? It's like saying, if I ask you what is a human, saying humans have a cardiovascular system. That's good, but I still don't know what a human is, right? You've explained a behavior or a characteristic, but what is a defining feature of an acid? Can anyone tell me? Structurally, when I give you a molecule as an acid, what part about the structure of the molecule tells you it's an acid? What can an acid do in water? Sid?
It ionizes in water.
So do salts. So what would make an acid different?
It dissociates hydrogen ions in water.
Yes, very good. So that honestly is a very good definition of acids. You'll learn very soon that that's not the best definition of acids. I think, Sid, you've learned that from your Module 6 assignment. But it's the best one to use until we get to Module 6, which is about acids and bases. And it's that acids dissolve in water to release hydrogen ions. Acids dissolve or dissociate in water to release hydrogen ions. What about a base? It's the exact same definition, but instead of hydrogen ion, what word are we going to use in front of the ion?
Hydroxide.
Very good. The OH minus, or the hydroxide ion. So guys, that is a definition of an acid and base. So what that's telling us is a general structure of any acid is HA. Okay, where A is whatever else is bound to that acid. And when it dissolves in water, it's going to release H plus and whatever else that acid is made out of. Perfect example here is you see ethanoic acid, where the A is just a CH3COO structure. It's written in this weird way where we don't combine the carbons together because it's telling you a bit more about the structure of that CH3COO minus, but we'll talk about that much later. For now, just know that is the A, that is a H. And so when it separates, you see the H here and you see the A minus, or whatever's left of it on the right hand side. What about a base? A base can be written as BOH. I like to write B because B for base, right? BOH, an example would be NaOH. When it dissociates in water, you get B plus and OH minus. So in the case of NaOH, you will get Na plus and OH minus. So guys, I want you to calculate or find out for me what is the K constant for each of these reactions. So for the acid, which is reaction 1, what is K equal to? For the base, that is equation 2, what is the K equal to? Hit the raise hand icon once you've got your answer. It should take you no longer than 10-15 seconds. Good. Like that speed. Good job. Is it only Jacob that's got an answer? Nikita, what's your K value for equation 1 and what's your K value for equation 2?
Is it A minus and then H plus?
Okay, I think what's made it hard for you guys is I haven't given you the states, which I apologize for, but you should generally know that all acids and bases dissolve in water, so they're all aqueous. Okay, so keep going, Nikita. So K for equation 1 is H plus times A minus divided by?
HA.
Yeah, easy, right? There's nothing crazy there, guys. That's literally what I was looking for, HA. Right, and what about for equation 2?
B plus and OH minus over BOH.
Good. Now, Rithani, you mentioned something about pH. So I'm going to ask you an additional question. What is the formula for pH? What is the formula for POH, if you know that? But start with pH. What is pH equal to, Rithani? Remember the formula?
Is it the log formula?
Yeah, it's a log one. Good. What is it?
I'm not too sure.
Does anyone know what the... Jacob, what's the... Actually, Sid, you're doing an assignment on acids bases. What is pH equal to?
That wasn't actually covered in my...
All right, Sid only covers what's in the syllabus dot points. All right, let's go to Ikshita. Any idea, Ikshita?
Was it log H something? Log H plus, was it?
That's all right. You guys gave it an honest go, which is what I care about. Good. Yeah, so pH is negative log 10 of the hydrogen ion concentration. The reason I'm telling you this is when it comes to acids and bases, we're crazy about hydrogen ions, and then POH, which is a measure of the concentration of a base, is negative log 10, the concentration of OH minus ions. So chemists are fanatic or crazy about H plus and OH minus. So whenever we get an equation like this, right, guys, where we have to remove all this stuff, or you get an equation with H plus A minus and HA, we like to rearrange it or rewrite it in such a way that we have everything in terms of hydrogen ions. And here, we like to write it in such a way that we have everything in terms of hydroxide ions. That's because we can actually measure with a pH probe or with an indicator, we can find pH. And from pH, we can start subbing in values, right? We can find the hydrogen ions, we can find the hydroxide ions. Key point here, we want to rewrite everything in terms of H plus and A minus. So I want to ask all of you, what is the relationship between the concentration of H plus and the concentration of A minus if I put an acid HA in water? Just think about it. I put 1 mole of acid HA in a liter of water.
They're equivalent.
Equivalent, exactly. So I can say they're equal and said, what about B and OH?
I could say the same thing.
Exactly. So what we like to write is we like to rewrite the K constant for acids as hydrogen. Since A minus is just equal to hydrogen ion concentration, we rewrite it as hydrogen ion concentration squared divided by HA. And you see now we've gotten rid of one more unknown, right? We don't care about the A minus. We want to write everything in terms of H plus. Since A minus is equal to H plus, just H plus squared divided by HA. And by that same logic, K here would be equal to OH minus squared divided by BOH. That is all this dot point wants you to know for now. Does that make sense? And all of you should remember from now on that pH is negative log 10 of hydrogen ion concentration, because it's technically, because of this dot point, it's technically part of this module and inquiry question. Okay, and this value here, when I put brackets, is just the concentration in moles per liter of hydrogen ions. Good. Now the last thing I'm going to say, guys, is we put little subscript abbreviations for the different types of K that we're finding. Since we're finding the K of an acid, we call it Ka. Since we're finding the K constant of a base, we like to call it Kb. We usually use lowercase, so I shouldn't be using capital A. You usually see it written in an exam as Ka and Kb. Okay? And then here, for salts, we write Ksp. SP because it stands for the word solubility product, meaning product of solubility. This is the product of solubility, like this entire reaction technically, right? It's a solubility reaction, and this is a product that's made that's not soluble. So solubility product is a term we use. Okay, so that's Ksp, and remember Ka for acids, Kb for bases. Good. Last thing I will say is, maybe it would be written here. Yeah. Kb, the word B in longhand form stands for base dissociation constant. It's the exact same as K. It's just other words you'll be seeing. They'll ask you to find. So they might give you a question and say, calculate the acid dissociation constant. You might go, what the heck does that even mean? They literally are asking you to find, in that case, Ka. The A in K stands for acid dissociation constant. I need you just to say this out loud, because if you don't say it out loud, you're going to forget it straight away, right? So Ka is acid dissociation constant, Kb is base dissociation constant, Ksp is a solubility product. They're all talking about the same thing, just some fancy words we like to use, okay? Good. Any questions so far? Good. I would encourage you to do whatever questions you'd like from this page here. You don't have to do all of them. Do a couple. If you feel confident, you can skip and just do D of every question on the second part, etc. This is from a textbook, so not as high yield as doing an actual exam paper. Good. Any questions so far? Good.
I have a question.
Yeah.
You know how we said that we can't add solids in the product constant, was it?
Yeah.
Yeah.
That's right.
Why is that?
Good question. So we went through this a couple of weeks ago. Let me just re-clarify, right? I just like to use thought experiments because it helps you really understand things, right? Solids and liquids, actually, they have a fixed density. And density is mass and volume. And density is concentration, right? So to give you an example, I can give you a cup of 1 mole per liter of acid. I can give you a cup of 2 moles per liter of acid, right? The acid that's 2 moles per liter has double the concentration in the same volume. The volume does not change, right? But since the mass or the number of moles changed, the concentration was double, or 2 moles per liter instead of 1. If I was to give you a solid instead of an aqueous substance like an acid, I can't give you a higher concentration of gold. The more mass of gold I put in your hand, the greater the volume that gold will occupy because it has a fixed unchanging density. And density is concentration, so arbitrarily for all solids and liquids, we just give their concentration is equal to 1. Does that make sense, actually, though? You can't increase the mass of a solid or liquid without increasing its volume proportionately. Whereas with aqueous substances, you can keep everything in 10 ml of water, but you can double the concentration of ions in it, etc.
Yeah, that makes sense.
Good question. All right, I want to get you guys to do maybe one more question, and then I will take you through solution equilibria. So I'll get you to do. Oh, this is a good question. Very good question. Okay, 2019 PEM. Do question 1 and question 20, guys. 1 will be easy. Little tip for you, a little exam tip. You have 20 MCQs in your HSC Chem. Question 1 is always going to be a warm-up easy question. Don't think too hard about it, right? Question 20, question 16 to 20, there'll always be one question that will be challenging, even for a Band 6 student. So for those questions, you need to think really hard about, am I making a silly mistake? Am I missing something or not seeing something which is going to cost me a mark? So for the second question here, think hard. First question, think hard, but just logically and fast as well. Okay, I'm going to give you about 3 minutes. So 4:46, go through the solutions. Hit the raise hand icon once you've got an answer. Okay, some water. Okay, what's our answer for question 1? Let's go with Akshita. Akshita, what was your answer for 1?
Was it D?
Why do you say D?
Well, I thought it was A or D. D.
Why do you think it was A?
Because you can see like there's a spike in on the graph.
Okay, is there a spike in only one substance or a spike in 2 substances?
There's a spike in both of them, so N2.
So could it be A?
It can't be.
Very good, right? So again, every time, like chem is the same. I'm going to be frank with you guys. It's the same stuff again and again and again, right? These questions do not get any different. Break it down the same way that we've always been doing it. Counteraction, so initial stimulus phase, which I'm highlighting in yellow, and then the counteraction phase, which I'm highlighting in orange. In the stimulus phase, we can see that there is an increase in concentration of 2 substances that cannot be explained by just the addition of NO2. So it has to be a change in pressure volume straight away. Okay. Temperature, there is no stimulus phase. Good. So we can straight away cancel out in a matter of seconds A and B. That leaves us with C and D. Now, with every LCP question, Ritanya, what are the 3 questions we ask ourselves?
Stimulus, opposite, and direction.
Good, right? You can literally do these questions with 10% brain power. You just go stimulus, opposite direction. What is the stimulus? That's what they're asking us. We've got no clue. What is the opposite? We don't know because we don't know the stimulus. Do we know the direction? Yes, we do. Actually, which direction did the equation shift after the stimulus phase? So in the orange phase there. Shita, did it go to the left or to the right?
The right.
Okay. You sound like you asked me a question. What do you think? Left or right? Which way did we go?
It shifted forward, so to the right.
Very good. So I just picked the product, right? N2O4, N2O4. What's happened to it in the counteraction phase? It's gone up. So of course we've shifted to the right. Okay, good. So now we've gone to the right-hand side. When it comes to pressure questions, just count the number of gas moles. There's 2 on the left, there's 1 on the right. So by shifting to the right-hand side, we favor the side with fewer gas moles, right? Or a decreased pressure. So what must the stimulus have been? An increase in pressure or decrease in volume. Which one is an option for us to select, Jacob? What did you get for 1? Jacob?
Yeah, wait. So D.
Good. I would have got D as my answer. Did everyone get D? Good. Good. Good job. Yeah. So as I told you, apply the same frameworks every single question. You will never go wrong. It's the second you start panicking and just trying to freeball it out of stress, that's when you make mistakes in chem, right? And unlike, doing a surgery or doing a high stakes banking or, coding for Facebook, for some very important algorithm, it's not that stressful in the moment, a chem exam, right? You've got 3 hours to do the exam. And you often don't need 3 hours. So take it slow, think through what would we have done in class if you're ever stuck on an exam question. Question 20 is a bit more challenging. Who's got, can you hit the raise hand icon if you've got an answer? Good. All right. What we'll do is, good, Ruthani's got an answer. Okay, so we'll do this question and then I'll give you all a 5-minute break. Okay? Good. So I'm not going to say anything. I'm actually going to ask you all because you know the answer. It's just all about thinking it through. So, Nikita, what's the first thing you do these kinds of chem calculation questions. You note that the equation has been given to you. What is the next step?
So there's two things, right? Because there's like 2 points. So you'd write up to it. So you'd do an ice table.
Good. But even before that, the first thing I would do is write my data. Right? It's always the same thing in my head. Equations, data. Do I need a diagram? Right. And I'll talk about framing the question very shortly. And have I found moles? So let's go through my little template. If you follow these steps, no matter how hard a calculation question is, you will 99.9% get the answer right. And the other 0.01%, you will be able to think it through by the end of the year. Okay. First of all, do you have your equation? Yes. Second of all, have you written down your data? What I mean by this is, do you have your C, your N, your V, so you can start thinking about which formulae to use? In this question, it's written in English. We need to write it in the language of chemical maths. Okay, so let's get Jacob. Jacob, I want you to use letters to tell me, what do we have for hydrogen, fluorine, hydrogen fluoride? So what are the C's, the F's, the N's that have been given to you?
Yeah, so you just got the C for all of them, right?
Yeah, so you can just put a C right here. So C, HF, and what time point is that, Jacob?
The initial, so the very start.
Good, so put CI. Good, so now we've got CI of all these gases, and that really fits into our ice table, right? All right, what else have we been given, Jacob, as our data?
We've also got the KEQ value, which is 313.
Good. So we know that KEQ equals 313. They've given it to us in chemical maths. They've also told you that the question is at the same temperature as KEQ. If they give you 30 degrees, that'll stuff you up completely. Because can you use this KEQ value, Sid? Can you use 313 if this system was reaching equilibrium at 30 degrees?
No, because the KQ would be different.
Very good. KEQ is temperature dependent, right? So this is very important because this is pretty much telling you, please use the K we gave you. That's what it's telling you, right? Otherwise, it wouldn't tell you the same thing twice. Now, the next thing is, do you need a diagram? For these kinds of questions in the beginning of Mod 5 Chem, we don't need any diagrams, right? One of the final things I asked myself is, have I framed the question? Framed the question. What this literally means is, if you were to get a portrait that you wanted to put on your front door in your room, with what the question is actually asking you, what would you write inside this box? What are they asking you for, everyone? Do not repeat this statement to me. Tell me in chemical maths, what are they asking us to find? Anyone? Anyone? So C of HF at E equals question mark. That is what this question is asking you, right? And the second you write this, you will start to realize how to solve this question. Okay? Now, to solve the question, you start working backwards, right? You think, well, for me to find C of HF at equilibrium, what would you need? Can anyone tell me, how would you get to concentration of HF at equilibrium? How can you find that? Sid?
You find the reaction quotient initially, and then you see which way the system must go to reach equilibrium.
Yeah, sure. So that's one plan of attack, right? There's a few ways to do this question, but that's what framing the question helps you with. Good. So I think most of us should have a plan of attack now. So if you need the initial concentrations of all the gases, you can straight away find Q. So what is Q when you sub all this in? So Q is equal to HF squared divided by H2 and F2. Sub in those values, you can straight away use them. What do we get?
I got 1,000.
1,000. Right. So now we know that Q is much greater than K. So which way do we need to go to get to K?
Reverse reaction.
Reverse reaction. So now we know the concentration of HF needs to be less than 0.500 moles per liter. Good. So we know it could be this, but 0.25 is less than 0.5. Could it be B? And could it be D? Because they're all less than 0.5. It's just the 0.55 is a little bit weird. Don't know where they got that from. So right now, D is looking a little bit funky because of the 0.55. It should be less than 0.5. So is it B or is it C? Now, what haven't we used to get to our answer that someone mentioned earlier that we kind of wrote here? Everyone? You could try a rice table, right? So what I mean by this is going to be a little bit harder and you probably will not be able to solve it. This is where you have to start thinking, right? We don't know the concentration of HF at equilibrium. We know the K constant. We know the initial concentrations of all these substances. Can we possibly find the equilibrium constant for some of them? You could do something along the lines of well, from what Sid's mentioned, Q is too big, the reverse reaction is going to be favored. Now, Jacob, if the reverse reaction is going to be favored, what's going to happen to HF? Is it going to increase or decrease?
It would decrease.
Good. So we know that HF needs to decrease by a factor of X, right? A factor of 2X to be specific because there's a 2 in front of it. And that means that F2 and H2 need to increase by X. Does everyone agree? So now we know the equilibrium concentrations for all the gases. For H2, it's going to be 0.012 plus X. For F2, it's going to be 0.02 plus X. For HF, it's going to be 0.5 minus 2X. And we know that the product has to be equal to 313. So you can go, well, K is going to be equal to HF squared divided by H2 times F2, right? Sub those values in. So 313 is equal to 0.5 minus 2x squared times 0.012 plus x, 0.02 plus x. Now, straight away, you can appreciate there's a quadratic equation. Do you need to do quadratics in chem? If you ever get to quadratics in chem, will you need to finish it off? Is it required knowledge? Actually, what do you think?
I think no.
No, people with general maths can do chemistry, so it's not. But I like to do quadratics, right? Because you'll get a definitive answer. Usually in chemistry, there'll be specific scenarios where you get quadratics, and they'll tell you round off one of the x's to 0, etc. Okay, but I would honestly just do quadratics and find out what is the x value, and then pick the option that best surmises that, especially for trials, just for peace of mind, because there's question 20 of a trial paper. But frankly speaking, is there another simpler way to do it? So you definitely will get an answer for x if you do it this way. You should. Is there another easier way, Sid? Sid, any ideas? So right now we're stuck between B and C, right, Sid? Is there anything else we can do?
I just tried and errored B.
Yes, exactly, right? So Sid, when you trial and error B, when you assume that B is the right answer, and you go, okay, well, let's assume the equilibrium constant of HF is now 0.25, which means a minus 2x change represents 0.25, and therefore an x change represents an increase by 0.125. 0.125. What do you get for K?
182.
182. Is that 313? No, right? So what is our answer now, Sid?
C.
Good. The trial and error kind of helps you out a lot with these questions too. I would have just done quadratics. I have committed so much to it already, but it's another great way to do the question. So your answer here is the 0.55 makes no sense, as we mentioned, so that cancels out, and that leaves us with C as our best answer. Good. Any questions with this one? The key point here is if you ever have initial and equilibrium constant, try doing a Rice table. Tip would also be if you've got a question and they're asking you whether it'll be at equilibrium or not, compare Q and K. This wasn't that kind of question. So you could have just gone straight into my way of trying to sub in all the values into K and finding HF concentration, and it would have led you to a quadratic. Okay. But the best answer here is C. So work through the process of elimination. We cancelled out A, B, D through elimination and B through trialing and erroring that option as the answer. Good. All right, guys, take your 5-minute break. We'll recap at about 5:08, 5:09. Stretch, get some water, go outside, and we'll jump back and we'll go into KSB questions. So hopefully by the end of today, we would have covered, I think, everything except the common ion effect. Okay, and maybe next week beginning we can do that, or if we're fast today, we can probably finish all of Mod 5. Good. See you in 5 minutes. Tanya, did you have a question?
Yeah, so I had a question from page 141 that I couldn't do.
Sure. How about we do that? We'll do that when we come back from the break. But what I'll do is I'll put it up for you. Okay.
Was that question 22, Rithanya?
Yeah.
Yeah.
This one. Which one? A, B, C, D. Which?
C.
C. Nice. We'll definitely do that. All right. I'll put it here. When we come back, we'll do 22, and then we'll do the rest of solution equilibrium. Good. Good job doing the questions and bringing it up. Okay, when everyone's back, can you hit the raise hand icon and we'll jump right into things. We'll do this question. I'm not sure, I recall with one of the trial questions for Mod 5, one of the questions weren't solvable. So I'm not sure if it's this question because there's a lot of papers here, but we'll see if we can do this one. All right, so question 22. Identify A, B, and C. How did you guys go with that? Sorry, Jacob, did you have a question or is your hand just raised?
Oh no, oops.
No, oh, good. Okay, cool. So Cl2, NO, NoCl. Do you guys want to give it a go? Which gases are which? So I'll start with Nikita. Nikita, what do you think A, B, and C are?
A is NO, B is Cl2, and then C is NoCl.
Good. And why did you say that?
Because like these two lines, they're coming from like the same spot.
Good. So from the same side, right? So when I see two lines that are increasing concurrently, they're both on the same side of the reaction, which tells me those two red lines are either Cl2 and NO. Now, the reason that one is twice the height of the other is due to the stoichiometric ratio, right? Remember we said the change in concentrations in reaching equilibrium follows the stoichiometric ratio. They were not at equilibrium here, they got to equilibrium here. So the change in concentration during that time should follow the 2-to-1 rule. So I can straight away say that this is NO and this is Cl2, and that leaves this with NoCl. Any questions so far? Good. We've done that. Let me just write it down for us all. We've been told that we've got NoCl, NO, Cl2. Next, explain the change that was made to the reaction time at 8.5 minutes. Right there. This one's a little bit harder because it's kind of like a student drawn, 8.5, but it's 9 minutes. 8.5 is right here. And there. Okay. So what do you guys think was the change that was made at that time? So Nikita, I asked you already. So how about we give Rithania? What do you think about 8.5 minutes? What's occurring there?
I said that there was a. Oh wait, no, I'm wrong. Okay, I think there's a change in temperature.
Good. Why do you say that?
Because
Is there a stimulus phase? Is there a sudden change in anything in that orange vertical line?
No.
It has to be temperature by default. That's literally the answer, right? Only temperature does not have a stimulus phase. Okay, good. Now, what was the stimulus? We don't know what kind of temperature change it was, right? So Sid, how do you answer this question about what was the change that was made? Let me just have a look at this question. They haven't told you whether it's endothermic or exothermic. You do need to know that. And the other silly part about this question is explain means cause and effect, and it's minimum 2 or more marks. They've put it as 1 mark in 4 lines. So as straight away you can see this trial paper is a little bit funky, but it is what it is. So we can say it's temperature, and I think when we don't have enthalpy given to us, so usually you would have done stimulus, opposite direction, right? But we don't have enthalpy given to us. What assumption can we make, everyone? This is only when you haven't been given the enthalpy. Got my homemade pearl milk tea. I'm drinking that. But let's go with Akshita. When you don't have information about enthalpy, what logical guess can you make based on the type of reaction you see?
I'm guessing it's an exothermic reaction.
Good. Synthesis is exothermic because it requires net particle collisions. So you can assume it's exothermic if they don't give you any enthalpy at all. And put heat here. And so which way did everything go? Let's go to Jacob. Jacob, fill out the stimulus opposite direction for us.
All right, so stimulus was an increase in temperature.
How do you know it was an increase in temperature?
Because, well, we know that it's increased because it's shifting left. So if it's increased, then it means it favors the endothermic. So endothermic.
Sorry, is it shifting to the right, Jacob? This is 8.5 minutes, right?
Yeah.
But what's happening to the product?
It's decreasing.
Good. So are we shifting to the right or to the left?
Well, if it's decreasing, then it means that we're going the reverse reaction.
Good. So that's to the left. Do you agree?
Yeah. Yeah.
Good. So direction is LHS. So then, yeah, keep going.
Yeah. So I guess the stimulus is increase, and then opposite would be decrease. So, and then yeah, direction left. So decrease in temperature for opposite.
Good. So you're going up the ladder, right? So you've been told the reaction shifted to the left-hand side because the product went down. That means we used up heat. And remember, the system is always trying to shift to the direction that achieves that opposite. So by shifting to the left-hand side, you can see that it's using up heat. So the opposite is decreasing heat. The stimulus is the opposite of the opposite, right? So it's an increase in heat, right? So pretty much quite literally, we're working backwards this time. That's it. So I agree. I do think it's an increase in temperature. Good. But again, silly question. They usually, in a HC exam, they will always give you enthalpy. 22C, let's quickly do this and then we'll get to KSB. Use the data from the graph to calculate the equilibrium constant for the reaction given at time equals t equals 6 minutes. Now that's stuffed because you don't have any values for concentration. Can't do this question. They haven't given you K. Okay. Assume the initial concentration of reactant C is 8.5. Okay, so guys, the way you would have done this question, let me show you, is you've been told that this is 8.5 times 10 to the power negative 2. Can anyone guess, how would you have solved this question? They're asking you to find K for the system. I'm guessing it's before the temperature change. Yeah, it's 6 minutes. They want you to find K at this point in time. Any ideas how you would have done that, guys?
Rice table.
See, the only issue with the rice table is you have no clue what the equilibrium constant is, and thus the change in concentration. But the way you can find that out, without even having to really do a rice table, you just measure the heights. So find out how many centimeters in your ruler this is, how many of a centimeters that is. That's equal to 8.5 times 10 to the power negative 2. Measure the height of all the other gases at equilibrium. Use your key, and you'll get their concentration in moles per liter. And then you just sub that into K. So that's what you would have done if you had the paper right in front of you. Does that make sense, everyone? Let's say this was 10 centimeters high, and that equal to 8.5 times 10 to the power negative 2 moles per liter. That means 1 centimeter is equal to 1/10 of that, right? And then you just use that key, measure the height of all the other gases at equilibrium, sub it in K. So Ruthania, that's how you would have solved it if you had the sheet, but Ruthania, you should have the sheet in front of you because you have the physical copy of the booklet, is that right?
Yes.
Just do it that way. The rest of you, when you get your booklet, do the same, but that's how you would have done it in the exam. It's hard to do it when it's just online on the screen in front of us here. Good. Let's move back to KSP. Okay, I want you all to have a look at this inquiry question. How does solubility relate to chemical equilibrium? And I want you all to try answering this question for me. I'm going to give you about 20 seconds to tell me the answer to how solubility relates to chemical equilibrium. Just dumb down words. Imagine your friend asked you this at school. How would you answer the question? Sid, whenever you're ready, just explain to the class how solubility relates to equilibrium.
So it's that if something is completely soluble in like a solution, it's not at equilibrium. But if it like partially like dissolves, then a dynamic equilibrium forms.
Good. I think you pretty much answered that question. Does anyone want to elaborate a little bit further? Jacob, anything else you'd want to add?
Yes, so if it's soluble, then that tells us that a precipitate will form, right?
If it's soluble or insoluble?
If it's insoluble, then it means a precipitate will form. Yeah. So, no, I was gonna go on with that, but never mind.
That's all right. Anyone else want to add anything else? Okay, the first thing I want you all to understand is there is no such thing as something being completely insoluble and completely soluble. Think of it more as every salt has a solubility point, right? What I mean by this is if I have 100 ml of water and I add sodium chloride versus lead chloride in 100 ml of water, it might take me 22 grams of sodium chloride to be added into water until I start seeing a precipitate at the next increment I add beyond 22 grams. Whereas with lead chloride, it could be that even after adding 2 grams of lead chloride, I start to see a precipitate form in the water. But does everyone agree 2 grams of lead chloride still dissolved? Being insoluble doesn't mean no particle will dissolve. All salts have varying solubilities, and all salts can be pushed to their limit. Does that make sense to everyone? So the words soluble and insoluble actually refers to cutoffs. When less than 1 gram of a solid can dissolve in a liter, we usually say it's partially soluble or insoluble. When it's more than 1 gram of a salt that can dissolve per liter, we put the arbitrary cutoff that it's soluble. Does that make sense to everyone? Right? So even within the soluble and insoluble category, there's a huge spectrum. Okay? And I think Sid worded it perfectly, that salts form equilibria when they dissolve, right? And they most specifically form equilibria when they're right before what's called their saturation point. So you can say salts can form equilibria in solution Does anyone know what saturation point is? Has anyone heard of that term before?
Was saturation point like in a liquid, if you, no matter how much solute you would add, it wouldn't dissolve because it's reached the maximum?
Yeah, you quite actually explained saturation point. So saturation point is the maximum amount of solid that can be added to a liquid before a precipitate forms. So now a little thought experiment above, I just arbitrarily made 22 grams as the saturation point of sodium chloride. I can add up to 22 grams of sodium chloride without seeing any precipitate at all. The second I add more than 22 grams of sodium chloride, let's say I add the next 0.1 gram, a precipitate will form immediately. Okay? The same with lead chloride. With lead chloride, how it's a different number. I can add comfortably up to 2 grams of lead chloride in this 100 ml of solution before I see a precipitate. At exactly 2 grams, I'll see a very, very faint precipitate. That is called the saturation point. If I add any more mass of lead chloride, you will see a clear precipitate forming. So again, to explain things to you, with a salt, there is a huge mass. So imagine this is an x-axis of the mass of salt that can be added into a solution. All right, there's a huge point until you reach saturation point, which is the max mass of solid that can be added to a solution without forming precipitate. Okay, and any additional mass past saturation point will form what's called a supersaturated solution, where you will see a clear precipitate. If you add any mass of salt that's less than the saturation point for that volume, so in 100 ml example is 22 grams of sodium chloride, if I add 10 grams of sodium chloride, it is called a unsaturated solution, and no precipitate forms. So my question to you guys now is, where along this axis do you see an equilibria form? Do you see an equilibria at A, B, or C?
B.
Okay, see this confident, got an answer. Tanya, what do you think?
B as well.
Sid, what do you think?
I think it might be C or B.
Okay, Jacob?
I'd say it's as soon as the precipitate forms. So I guess B.
Would it be B or C, Jacob?
Well, where a precipitate forms would be C, I guess, but
Nikita?
B
no, it is B.
and C.
The answer is B. Okay, so salts form an equilibria when they're saturated. So the only thing I wanted to add here was that saturated salts can form chemical equilibria in solution. Okay, so the point I'm trying to make here is that point when you've added the maximum amount of salt to a volume of water, just when you can see a faint precipitate, that is called saturation point, and that is when a salt forms a chemical equilibria, right? For some salts, adding even 0.01 grams in 100 ml will form that equilibria, and so we call them insoluble, right? For other salts, you can add 20, 30 grams before you form that equilibrium, right? And since more than 1 gram per liter dissolves, we say it's soluble. Okay, so for saturated salts, they form equilibrium solution. And make sure you all jotted down, or at least wrote down the points, what saturation point is. So anyway, we haven't touched upon the dot point, so don't worry about everything we've learned. If it didn't make too much sense, we'll come back to it very shortly. For now, let's start by going through the key dot points here. So first of all, what are the processes involved in the dissolution of ionic compounds in water? Nikita, can you define what an ionic compound is again?
A metal and a non-metal. No, wait, it was a cation and an anion. Yeah.
And what's the bond between them?
The electrostatic forces, ionic bonds.
Very good. Right. Electrostatic forces of attraction. Nikita, are they strong or weak, the electrostatic bonds of attraction?
They're like, they can be like broken with like water, like when they like, cause like they collide, like the like charges collide and then they like repel.
Good, but you kind of gave me a politician answer. What I mean by that is, for strong or weak, you gave me an example, but you didn't answer the question as to whether they're strong or weak, right? So, Jacob, strong or weak ionic bonds?
I'd say they're weak.
Okay, I think that's a logical answer, but I'd say it's actually not the case. Ionic bonds are very strong, right? The way you think about it is, maybe if you want, go get some salt after class, put it on a cooking pan and put the heat on the pan up, and look at what temperature it takes for that salt to melt, versus with sugar, which is not an ionic compound, right? Put sugar on the top and see how long it takes for the sugar to melt and caramelize, and it'll be a much lower temperature. The point I'm trying to get at here is that ionic bonds are very powerful, and we'll talk about why something as weak as water can break such a powerful bond shortly. Okay, but for now, I want you to remember there's strong electrostatic bonds of attraction. Okay, good. So the key thing that you're seeing here is that the ionic lattice, which is that it consists of oppositely charged ions bound together by strong electrostatic forces of attraction. You need to be ready to label the bonds and explain that all the ions are oppositely charged adjacent to one another. Good. Now let me ask you this: why do we write, methane as CH4 and ethane as C2H4, etc., whereas we write NaCl as NaCl, even though there's, why don't we write it as Na9999 Cl9999? Because there's millions of sodium atoms, millions of chloride ions. Whereas even when there's 2 atoms of carbon and 4 atoms of hydrogen in an organic compound, we add the 2 and 4. So why do we denote ionic compounds in this way, where we put it in their simplest whole number ratio rather than their actual number of atoms? Anyone know what the names of these 2 types of notations are called? When we write H2O or C2H4.
Is it empirical?
Exactly, right? So the point I'm trying to get at here is for molecules, aka compounds that are bound by covalent bonds, we put the exact number of each element in the molecule. So if there's 10 carbon atoms and 20 hydrogen atoms in a molecule, we'll put C10H20. For ionic substances, they consist of an infinite lattice. There is an infinite number of sodium, infinite number of chloride. Not actually infinity, but just a huge, huge number that's just unfeasible to ever write. So write it in the simplest ratio. It's just important to understand that, okay? So molecules are in molecular formula. Ionic substances are in empirical formula. Let's briefly talk about the properties. Now, you would have learned this in properties and structure of matter, so module 1. So I'm going to start with Nikita, high or low melting boiling point? Why is that?
Ionic substances have a high melting point because their bonds are strong, like their intermolecular bonds are strong.
You're perfect until the third last word, intermolecular bonds. The word
is intra.
Yeah. Okay, let me explain this, guys. When you talk about inter and intra molecular bond, the second word you all use was molecular. That refers to molecule, aka covalent bonds, right? You only ever talk about intramolecular bonds and intermolecular bonds when you're talking about covalent compounds. When you're talking about ionic compounds, when you're talking about metallic compounds, you cannot use the word intramolecular, intermolecular. The molecular part is incorrect. Does that make sense to everyone? Okay, so I would just call it strong electrostatic bonds of attraction between ions. So intermolecular bonds are between molecules. intramolecular bonds are within molecules. So an example of that is H2O, right? The oxygen and hydrogen are bound together by strong intra or within molecular bonds, and other H2O molecules are bound to each other by inter or between molecular bonds, right? You don't use that word when we're talking about ionic substances. But good, Nikita, the answer was right. Strong electrostatic bonds require a lot of energy to overcome. Rithanya, on to you. What's another property? Are they conductive or non-conductive ionic compounds? Rithanya?
They are.
Conductive? Rithanya, I want you to imagine that you're walking down the street and there's a puddle of salt water. There's a live electrical wire in that salt water. If you accidentally stepped in that puddle, would you be electrocuted? Yes or no?
Yes.
Okay. What if you stepped in a puddle of pure distilled water and there was a wire of live electricity inside that puddle? Would you be electrocuted? Distilled pure water. Britannia?
Yeah.
You wouldn't. So guys, what I'm trying to test here is whether you understand what conductive means. Conductive means that the compound has freely moving charges. The solution or whatever it is has free moving charges which enable it to conduct, right? Conducting electricity just means charges are moving within that compound. Now, if you look at an ionic substance when it's solid, nothing is moving. If I pass a current through here, if I bring a negative positive end here and a negative end here, or run a current through it, this ion cannot move. It's stuck in place in the lattice. When I dissolve the salt in water, then everything is broken apart. And then you have positive and negative charges moving around everywhere, and there'll be a net movement when I apply electricity. The simple answer here is ionic substances do not conduct unless those electrostatic bonds are broken. And the only time those electrostatic bonds are broken is when you melt an ionic substance, in which case it becomes molten, molten meaning melted, or in water. Water has the potential to dissolve ionic substances too. Okay, does anyone have any questions about the properties of ionic substances? Those are two things you need to know. I don't care about whether you understand brittle or malleable or any of that stuff. Key thing you need to understand is the melting boiling point and the conductivity. Sid?
You know how we were taught that ionic bonds had like a sea of delocalized ions or electrons?
That's metallic bonds, but yeah.
Oh, it's metallic. Okay, yeah. Okay.
So metals consist of positively charged metal cations, like magnesium, and around them is a sea of delocalized electrons. So metals will conduct even when they're a solid. Ionic substances, examples are salt. You can't run electricity through salt. You can run electricity through salt water because the salt or the ions are now free moving. They're not caught in a lattice because they've all been broken by water. Makes sense? And another time where ionic substances would conduct is if I melted salt into a molten state, then I've broken all of these bonds as well. Yeah, they're free moving charges. Actually, the question?
Yeah, so you know how you said that magnesium ions, and I just had a question. If magnesium was solid, right, and you said it was in a lattice structure, how does that conduct electricity? Does it conduct electricity?
Ashita, what is a lattice?
Like a structure, like a firm structure, kind of.
Lattice means regular, right? Amorphous means irregular. Those are the two opposites of the same word, right? So lattice just means regular structure. Doesn't tell you much else. The reason an ionic lattice cannot conduct is because there are ionic bonds holding every single ion fixed in place. It cannot move. There's a bond here, a bond here, a bond here, a bond here, that this ion cannot move, right? That is very different to a metallic lattice A metallic lattice, lattice just means order, which means the metal cations are in order like this. Right? But the electrons, remember, magnesium, the nucleus of an atom is huge. The electrons are tiny, they're like little dots, like little flies around people. The people stay still, but the electron, these little flies, are always going to be moving around in every single direction. But more or less, it remains in this organized structure. Do you see that? Does that make sense, actually, though? So that's why it's called a lattice, because it's orderly, but it has free-flowing electrons versus the fixed ions here. Hence why metals conduct and ionic substances can't when they're solid.
Yeah, that makes sense.
Nikita, question?
Yeah, so you know how you said like in water, like if you put the electric current in water, it won't like do anything. Like what about like when you like if you take like a phone into the shower or like into a bathtub, and then how does it electrocute?
What do you think about tap water? Is that pure water, or is it being filled with ions like magnesium, calcium, fluoride?
I hope not.
It's got metal ions. It's got metal ions, right? So tap water, shower water all has small amounts of all these different metal ions. Have you guys ever washed your hands or brushed with toothpaste, and you start to see scum forming on the sink? Scum it's not dirt, it's just metal ions are precipitating with compounds in the toothpaste, etc., and they form this slight discoloration that you can wash off. If you search scum, you'll see what I'm talking about. If you don't clean bathrooms, every bathroom would get scum, and that's because there are little metals or ions in water. It's very hard to find distilled water. You'll only find that in chemical labs, etc. You won't find that coming out of your tap. And that's why you can still get electrocuted if, for example, a toaster falls in a body of water in the bathtub, etc. Okay.
Okay.
Good. All right. Now, let's start talking a little bit more about water. Now, for water, you guys need to know how to draw the Lewis electron dot diagrams for water. Now, key thing you need to remember, oxygen, how many electrons does it have, Jacob? Jacob, oxygen, how many electrons does it have? Akshita, how many electrons does oxygen have?
Can you hear me?
Yeah, I can hear you.
Does it have 8?
What number is oxygen on the periodic table, Jacob?
8.
Good, right? So since it's got 8 electrons, there's 2 electrons in the first shell. How many electrons in the second shell?
6.
6, right? So remember, whenever you're doing Lewis electron dot diagrams, you always only talk about the valence electrons, or the electrons in the outer shell, right? So you've got 6 electrons in the outer shell. Remember, electrons love existing as pairs, little married couples, right? So what you'll see happening is there'll be one lone pair of electron here. There'll be another pair of electrons here. And what ends up happening is when the oxygen combines with hydrogen, they share electrons. What kind of bond occurs when you share electrons? Britannia? What kind of bond do we get when we share electrons?
Hydrogen.
Covalent, metallic, ionic. Pick one.
Covalent.
Good. Covalent is sharing of electrons, right? And ionic is when you get a complete transfer of electrons, right? Where the metal will give its electrons to the non-metal. Okay, very good. So you get a covalent bond forming there. And now when you count the electrons that each atom has, they all have a valence number of electrons, right? Hydrogen has 2 electrons. Remember, hydrogen only has 1 inner shell. The inner shell fills to 2. So hydrogen is happy. This hydrogen's happy. It's got 1, 2 electrons. And when you look at the oxygen, everyone, how many electrons does it have? 1, 2, 3, 4, 5, 6, 7, 8. So everything is in a stable octet configuration. And by now you should of course know The goal of every compound in chemistry is to reach the magic 8, or the stable octet. Any questions so far? Good. Now, who remembers valence shell electron pair repulsion theory, or VSEPR theory? You don't need to know it well, but do you remember learning it? Okay, good. As long as you remember learning it, I'm happy, because the main thing you'll need to remember is that water carries a bent molecular shape. That's the word they want to hear in exams. If they ever ask you what is the shape of water, it's bent. Okay, that's because it has 1, 2 lone pairs and 1, 2 bonded pairs. So whenever you see 2 lone pairs, 2 bonded pairs, bent shape. Very good. Good. All right, let's come back to this and let's talk about now. Now you all understand the structure of water. Now hopefully you also understand shape of a lattice, especially an ionic lattice. Just before we talk about how water interacts with the lattice, guys, what happens with adjacent water molecules? All right, so say I've got 2 water molecules like this. First of all, Sid, is water a polar molecule or a non-polar molecule?
They're polar.
Very good, right? Now, what does polar mean, Sid? Can you just remind the rest of the class?
There's an uneven distribution of charge.
Perfect, right? So there's an uneven distribution of electrons or charge. Now, Rithania, which end is positive, which end is negative in water?
The hydrogens are negative. Oh no, positive, sorry.
So the way you think about it is it's all to do with electronegativity, right? And electronegativity, what it means is how hungry an atom is for electrons. An atom is more electronegative or hungrier for electrons when it has more protons. So Nikita, who has more protons, oxygen or hydrogen?
Hydrogen. No, wait, oxygen.
Hydrogen has?
Oxygen.
Good, I'd hope so, right? Because oxygen has 8, hydrogen has 1, right? So oxygen has way more protons. It's going to pull the electrons in this covalent bond. Even though it's meant to be shared, the electrons will sit closer to the oxygen. And what ends up happening is if I was to draw the electron cloud, the electrons would close around oxygen and there wouldn't be much electrons around hydrogen. So the way we denote that is we write this little sign here to show it's negative and here to show it's positive. And then, as you know, positive or opposite charges attract. And does anyone know the name of the bond between water molecules?
Hydrogen bonds.
Good. Is it inter or intramolecular?
Inter.
Very good, because it's between molecules, right? So it's the strongest of intermolecular forces. The other two being dipole-dipole, and the weakest being dispersion. Very good, right? Now, this is important to know because it's going to affect how water interacts with a lattice. So let's say you get a bunch of ice cubes, not ice cubes, a bit of salt, right? A tablespoon of salt, and you put it in a cup of water. What immediately happens is the second this lattice hits water, water molecules will bind to and be attracted to the lattice. Now imagine in NaCl, the negative anion is Cl minus. And what ends up happening is with the negative ion, the hydrogen end, which is positive, as you can see up here, the hydrogen end is positive, is going to be attracted to the negative end of the lattice, which is a chloride ion, and they're going to form bonds. Does anyone know the name of this bond that's going to form between an ion and a polar molecule? Nikita?
Is it polar dipole ionic dipoles?
Yeah, that would pass. I'd give that the mark, but we call it ion dipole bonds. Okay, and it makes sense because we're forming a bond between an ion, which is a chloride ion, and a dipole. Well, what does a dipole mean? A dipole means a partial charge, right? So like Sid said, an uneven charge distribution. In the case of water has a few dipoles. A dipole is represented like this, right? So here, this is a negative dipole, which I've shown you, and here's a positive dipole. And we often show it like this. We draw a little arrow to show the dipole. The positive end represents the positive end of the molecule, and the arrow tells you where the electrons are transferring to. Okay? In the case of water, there's two dipoles both facing towards oxygen. Okay? But yeah, dipole means slight uneven charge. Oxygen will have a negative dipole, hydrogen a positive dipole. So since we're forming a bond between an ion and a dipole, it's called an ion-dipole bond. I want to preface this. If you do not mention this word, ion-dipole, you will straight away lose a mark whenever it comes to any question about salts and water dissolving. That is a very, very high yield term to use. So make sure you highlight, underline it, exclamation mark. You must use it in your exam answers. Okay. So now, Nikita, and I think Jacob also justified that electrostatic bonds should be weak because water, which is a weak molecule, right? It's got weak hydrogen bonds, can break the powerful electrostatic bonds between ions. Can anyone explain why that's not the case? Or how, can anyone explain how these weak hydrogen bonds can break the powerful electrostatic bonds? Nikita?
Okay, so basically, the orderly array, it like gets disordered, and then the like charges repel, and then that it just shatters.
Close. I get where you're coming from, but it's not exactly answering the question, which was how do weak hydrogen bonds of water molecules break powerful electrostatic bonds? You did mention it's going to disrupt the orderly arrangement, which is true, but I'm saying how do these weak bonds disrupt that orderly arrangement, Sid?
Like a large amount of hydrogen, like atoms, like all like bond together with the chloride ion.
Good. Yeah. It's kind of like, I don't know if your friends, anyone has silly friends, but I remember being in high school and I used to get asked questions like, would you rather fight, one little dwarf or, one big dwarf or hundreds of little dwarfs, right? Which is all about power of numbers. It's the example is seen right here. If you get hundreds of hydrogen bonds, thousands of hydrogen bonds and surround one ion, it will be pulled off the lattice because 1,000 hydrogen bonds in cumulative sum are stronger than one electrostatic bond. And that's exactly what happens in water. Guys, what you're seeing here is not a clear depiction, it's a model. The limitation of this model is water is actually much smaller and chlorine is actually much, much larger. Chlorine has 35 protons, right? No, sorry, it should have 35 as its mass number, 35.45. It should have 17 protons, 17 electrons in 3 shells. Remember, every shell you add, it gets much, much bigger. So my point being, there's a lot more ion dipole bonds that form than you see here. In this image, it shows you 3 ion dipole bonds for every ion. In reality, it's hundreds, thousands. So that explains why water, which is so weak in terms of its bonding, can actually rip apart such a strong lattice. Good. Now, this is a part which I believe Nikita was referring to, which is all about the arrangement that is formed after the ion is broken off the lattice. Okay? The name of these structures are called hydration spheres. And let me just show you. This is exactly how your exam, this is straight copy pasted from a sample answer from the HSC papers. The second that an ion is broken off the lattice, we form what are called hydration spheres. And you can see how the water molecule is arranging itself. They arrange themselves in such a way that the positive dipole faces the negative charge, and the negative dipoles face the positive charge. And in reality, it shouldn't be shown. So this is completely correct. But if I was a student, I was to write my answer for potassium when it was broken, it would be something along the lines of this. I draw potassium like this, and I draw oxygen here, oxygen here, oxygen here, oxygen here, and all the hydrogens. And I'd show this. And I'll also show the lone pairs. And finally, I'd show the bonds. Now, what is the name of this bond, Rithania, that I've labeled? Tanya, what?
Ion dipole.
Very good. Ion dipole bond, right? And do you see how in the sample answer diagram they've labeled the ion dipole bonds as well? To show you how high it is to make sure you do that. Okay? So key things is make sure the water molecule is oriented correctly. So it should be facing with the hydrogen end facing the negative charge, the oxygen end facing the positive charge. This is not as nice. It's technically not as correct either. You want to show it like this and like this. Okay? Do we have any questions so far with how to draw these hydration spheres? Good. Well, now you will understand exactly what happens with an ionic lattice when it dissolves in water, right? So actually, to give us a quick summary, what does happen? While you're doing that, we'll move on to the next dot point.
So we have water molecules, and they have their, the hydrogen, was it? And the hydrogen affects the substance that's being dissolved into the water.
Yeah, I'll pause you there. I understand you guys get it, but do you see the hard part is wording yourselves in a clear, articulate manner, which is why I want you guys to make sure all of you, every time before you come into class, you've looked at the notes, you try to teach it to yourself, right? This is new information, so I think Ashita, you did a great job. It's just I'm making a clear point. It's almost a separate point that when you're learning new concepts, work on how to articulate it as much as you work on how to understand it. Now, I'll just word it for us just in the interest of time. So the key points there was that an ionic lattice consists of oppositely charged ions with strong electrostatic bonds. Water molecules will form ion dipole bonds and disrupt the lattice structure. You'll then form hydration spheres with those ion dipole bonds that ensure solubility, and they prevent the ions returning to the lattice. I think that's the most important point as well that I did not stress, which was the role of these hydration spheres is, do you see how it's blocked off or quite literally imprisoned the chloride ion? The chloride ion cannot jump back into the lattice. And in your visual eye, what you see is you see the salt disappearing before you, right? So when a salt disappears when you add it in water, what's actually happening is it's being pulled away by these water molecules, imprisoned in these hydration spheres and trapped, can never return back to the lattice. But when does it return back to the lattice, everyone? When does this chloride ion return back to the lattice? There is one circumstance. Can anyone tell me? Sid, do you want to explain it to the class?
Is it when water is heated and then evaporated?
Yeah, so technically you're completely right. I didn't think of that, but yeah, if you evaporate water, there's not enough water to form these hydration spheres. But what else can you do to make sure there's not enough water? Nikita?
Add more salt, like super.
Perfect. Exactly. When you super saturate a salt, there's not enough water molecules to tie up every single ion in a hydration sphere, right? So let's imagine you have a saturated solution, right? So in a saturated solution at a molecular level, what's happening is every single ion is being surrounded in a hydration sphere. And the second you add an additional ion, these water molecules either have to stay here and allow this precipitate to form, but this will not be surrounded by a hydration sphere and will form a precipitate, or they'll need to jump to this ion, which allows this ion to form a precipitate, right? And that actually continually happens. A precipitate is a dynamic process. There are always ions jumping out of the solution, and there are always ions that are jumping into the solution, even though it just looks like a solid precipitate is formed. But that is exactly what's happening. So very important point Nikita mentioned, which is in a supersaturated solution, there's not enough water to form sufficient ion dipole bonds and keep ions in a hydration sphere to remain soluble. Good. You don't need to know the solubility table for now. Have a look at it in your own time. Now, this graph, there's only one thing you'll need to know, which is the general trend in solubility with temperature. Of course, there are exceptions, and I'm sure we can see the exceptions here. But Jacob, what is the main trend that you can see that happens to solubility with temperature?
Is it like that? Is it something to do with nitrates?
Don't worry about nitrates, and
Okay.
just generally with these salts, as temperature goes up, what happens to solubility?
It increases.
Good, right? There are exceptions. NaCl is barely going up. Ce2SO43 is going down, but majority of salts you encounter in the HSC, their solubility will increase with temperature. Okay, the reason for that is when you increase temperature, there's greater energy to break those electrostatic bonds. It's easier to break up the ions into hydration spheres. Okay, that's a general trend. So just keep that at the back of your mind. Good. All right. This dot point here, you just have to remember the key points here, right? They're like bringing this up because it tests who knows their syllabus versus who just attends class and learns whatever the teacher shows them. Sometimes teachers will skip this content. It's about the cycad fruit. And the key point they're trying to get you to understand with this dot point is that the indigenous peoples used principles of chemistry in eating this cycad that we only discovered hundreds of years later after well-founded theories about ionic substances, right? So what you're doing in this dot point is you're applying chemical principles of equilibria to understand why the First Nations peoples use these certain techniques to eat the toxic cycad seeds. So here's a cycad plant. I might have seen it before. I don't know because I'm not a botanist, right? You might have seen it before, but it's an Australian plant. The seeds are nutritious, but they also have the toxin cycassin. Now, a very important principle or property of this toxin that you see here called cycassin is that it has a very high solubility. So that's all I want you guys to write for now. Don't worry about the number, the solubility number. As long as you can jot down cycads, cycassin, toxin, high solubility. That is a chemical property that we are now going to optimize and use. Now, what ends up happening is, draw it for you here. So here's a cycad seed. And what they did was they put cycad seeds in woven baskets. Imagine a basket that's very porous, made out of straw, like this, right? It's cool straw design. Okay, and these seeds would sit inside. This is a seed. Would sit inside the basket, and they'd place the basket in running water in a stream. So what ends up happening is water is always running into the basket, washing the seed, and then running out of the basket. Okay, and I don't know how they knew this, which is pretty interesting. But the cycassin toxin, it actually forms a chemical equilibria between its solid state and its aqueous state. You don't need to know any of the chemicals, guys, as long as you just write a general equation like this. AB forms A plus, B minus, right? Now, you form this dynamic equilibria. Whose principle must it abide by? Nikita, when you form a dynamic equilibrium in chemistry?
LCP.
Good, right? Now we're running this toxin or the seed which contains this toxin AB. I'm going to call this cycassin, right? We're putting it through running water. So what's going to happen, Ritanya, to the concentration of A plus and B minus if this cycassin toxin is always being washed away by running water?
decrease?
Good, right? So the running water is going to cause a decrease in the concentration of the aqueous form of the toxin. The solid form stays on the seed, right? The aqueous form gets depleted. And so the opposite of that is increasing the concentration of the aqueous form of the toxin. And so which way does the equilibrium shift, everyone?
Left. Right.
Right-hand side, right? It shifts to the right-hand side. And what ends up happening is a solid cycacin in the toxin gets leached away into its aqueous form and removed by the running water. So after doing this for a couple of days, the cycad seeds would become non-toxic, safe, and ready to eat. Now think about this. These people were doing this hundreds, potentially thousands of years before we even knew anything about Le Chatelier, chemical equilibria, etc. Right? So that's why this dot point is all about. Understanding certain principles that we historically used that are actually very logically based in chemistry. Okay, good. So this process is called leaching, right? They cut the seeds, put it in these woven baskets, let running water remove the aqueous form of the toxin, and that would shift the equilibrium even more to the right and minimize the toxin content of the seeds. Good. Two other things that they did is they would also cook the cycad seeds, so that would destroy the toxin, right? Because very high temperatures would cause chemical reactions to decompose the toxin. Another way to decompose the toxin is instead of using heat, you can use enzymes from fungi, bacteria, etc. So they'd also sometimes dig the seeds deep into the soil underground, leave it there for a period of time, and that would ferment or break down the seeds and the toxin as well. Okay, and then after that cleaning and cooking, it would also allow it to be eaten too. Okay, so the three things you've learned are leaching, which is what you're going to be using, which is grounded in chemistry, then also heating and cooking, and then fermenting the seeds as well. And the latter two are both used to degenerate or destroy the toxin. Good, so I've written all of this here. You do not need to know anything about the structure of the cycad seed, nothing about B-methylamine or L-alanine. I just wanted to include it for extra information, but that is all fine. Any questions? So have a look. This is like a typical exam question you'd get. You realize how easy these questions are. It's just you either know it or you don't know it. Hit the raise hand icon once you've got an answer. Easy, right? So Sid, what's your answer?
C.
Good, right? We can move on to the next question. Quite easy. Good. As long as you guys know this is a dot point and this is what they want you to know. Very good. Can help investigate the solubility rules and predict composition of substances when two ionic solutions are mixed. Okay. We'll probably have to go through these dot points next lesson. But what I'd want you guys to have a read of before we start next week. Next week, I plan to finish all of Mod 5. Is have a read of page 114. And try doing the questions if you can as well. Up to page 123. So 114 to 123. And I'll have a look at that next week. I'll pick some random questions and we'll go through them together. Okay? Good. Good. Does anyone have any questions so far? Okay. So like I said, Mod 5 is one of the shorter modules, so we finished a little bit early. And that's good because then we can start going through Mod 6 as well. Other tips I'll give you guys is make sure that you grind it out these holidays in terms of work, right? What you realize is a lot of people get a bit shell-shocked by first term of year 12. And then by the time you come back in Jan, the competition does get a little bit more intense, especially for those of you wanting to get into those very high ATAR courses, which unfortunately happen to be so, like medicine. Even law, for example, you can go to like Western or Wollongong, which have a lower ATAR. and that slightly affects employment. But if you work hard, you can work your way out of it. But I'd say the hardest ATAR courses is literally those of you wanting to do medicine. You have to make sure you grind to get the highest possible ATAR. The rest of you just aim to get that cutoff 2 marks above and work backwards. Maybe go to your teacher and ask them what mark you'll need to get and what rank you should probably be in that subject, like biology, to get the ATAR that you want. And they can help you out and guide you with that. Okay? Good. All right, guys. I'll see you next week. Okay? Have a good week. Good luck with any assessments you have.
Thank you.
Bye, Jacob.
I had like a question to ask you.
Yep.
So I'm on 12 units right now, and
Yeah.
I'm thinking of, well, I have 2 scenarios which I want to do, which is either drop one of the subjects or keep it just in case. So I'm doing PDHP and business. So those are the 2 subjects that I'm thinking of dropping. And